Hello and welcome to the third in a four-part series of videos presenting some exciting new applied watershed science from the Susquehanna River Basin Commission and our partners. If you haven't watched the overview video that summarizes this project, we recommend you do that now. In this video, we will provide a detailed look at our data collection and data analysis techniques, as well as the final results. Through this project, our partnership ultimately uncovered new insights about causes and effects of water pollution, and specifically that many types of water pollution are related to hydrologic alteration. Hydrologic alteration is a term that refers to changes in the way landscapes control and influence water, and especially precipitation. Given the importance of landscapes as an idea here, geographic information science played a large role in developing data for this work, so consider viewing the GIS video for more details on those specific methods. In 2010, the Susquehanna River Basin Commission launched its Remote Water Quality Monitoring Network, a series of 60 in-stream sensors that measure water quality metrics at set intervals for sites in Pennsylvania and New York, and report the data back to the Commission's website via cellular communication in real time. Because the original intention of this project was to examine water quality in areas impacted by unconventional natural gas, the sites for these sensors were all selected to intersect that part of the basin that is underlain by the gas-rich Marcellus Shale Formation. The sensors were securely fastened to stream banks and beds in locations that always remained underwater, and a solar panel, communication hardware, and other components were placed nearby on the stream bank above the flood height. Each monitoring station measures a host of water characteristics: pH, dissolved oxygen, specific conductance, water temperature, and most notably turbidity, an effective surrogate for excess suspended sediment, the subject that became the focus of this work. The overview video provides more information on turbidity in sediment and how excess sediment can be harmful to streams. The sensors measured turbidity at 5-minute intervals around the clock 365 days a year. This level of continuous data collection resulted in more than 105,000 data points per year for each station, and that's just for turbidity. For scientists, a large volume of data is a valuable and welcome resource, but massive data also introduces some challenges. It simply wasn't practical to use every data point, so we had to develop a method to screen and process the data into a usable volume, all while maintaining the data's explanatory power. To begin, we considered the wide variety of causes of excess turbidity. Turbidity can rise due to fish and animal activities, high stream flows, human activities such as recreation and construction, or natural plant cycles. The most profound effects on turbidity, however, are due to changing seasons, changing weather, and changing landscapes. Based on what we know about the scientifically documented factors that cause excess turbidity levels in each season, we decided to focus on summer measurements. Ultimately, we settled on using the mean turbidity value calculated from each station's records for the months of June, July, and August in 2010, 2011, and 2012. We confirmed this selection through trial and error testing involving 6 continuous monitoring stations, which we'll describe in more detail later. While we had data available for 60 monitoring sites, we ultimately selected 16 for more detailed analysis. These 16 sites effectively represented the range of conditions expected within the larger Susquehanna watershed. These watersheds ranged in size from 13 to 55 square miles. Now we're going to briefly discuss some of the statistical analysis methods we used. We're going to keep the technical jargon to a minimum and focus on the practical interpretations revealed by the analysis. Recall that our original goal was to relate unconventional gas activity to excess sediment in streams. Like most scientific studies, we set out to identify and statistically demonstrate a cause and effect relationship between these two variables. That is, we wanted to know if in-stream turbidity, the effect or response variable, could be explained by specific causes or predictor variables. Because changes in turbidity may be caused by many things, we screened a wide variety of predictor variables. One of the first things we had to figure out was which turbidity value best allowed us to distinguish among some of the known cause predictor variables. To accomplish this, we utilized a technique known as analysis of covariance, or ANCOVA. ANCOVA is a statistical test useful for examining a single effect against an array of cause variables. Using ANCOVA and the 6 test stations, we tested several different ways of summarizing summer turbidity data against a large group of cause variables. The testing pinpointed that the best way to summarize the turbidity data was by simply calculating the average summer turbidity measurements. The ANCOVA tests also indicated that stream flow, physiography, and man-made landscape change each cause turbidity to change. This confirmed what we already suspected. Scientists know that turbidity often changes when stream flow changes, and that other features of a watershed, such as geology and natural history, collectively termed physiography, also influence turbidity. Scientists also know that turbidity changes because people change the landscape, an idea further refined by this study. Armed with the information gained from ANCOVA testing, our next step was to use another set of statistical tools called General Linear Regression Models, or GLM, to test just how much influence each cause variable exerted upon in-stream turbidity levels. Our first effect variables describe natural gas infrastructure in select watersheds and across time. These variables describe the percentage of the acreage of the watershed occupied by well pads, or the density of well pads in the watershed, among other things. The R-squared value shows the strength of the relationship between turbidity and the tested metric. A value closer to 1 indicates a stronger relationship. We use the percentage of forest in the watershed as a benchmark because that value has a well-understood relationship with in-stream water quality. More forest in a watershed is generally associated with a healthy, unimpaired watershed and higher water quality. We were surprised to learn that none of our initial metrics explain the observed turbidity measurements very well. The GLM models produce low R-squared values indicating weak relationships. Accurately defining unconventional natural gas variables was an arduous manual process, and this, coupled with the poor statistical results in the 6 test watersheds, caused us to shift our focus to more general processes that impact forest hydrology. Next, we explored a GIS-derived metric called the Topographic Wetness Index, or TWI. The GIS video provides more detail about this, but in summary, the TWI identifies where water will flow across the land when it rains. Our hypothesis was that higher turbidity would occur in watersheds where the TWI flow paths intersected the largest amount of unconventional natural gas disturbance. This too was a poor predictor for observed turbidity in our study streams. The fact that none of these metrics worked well was perplexing because a lot of these watersheds are quite forested, and even after trying to account for natural gas infrastructure, physiography, and other factors, there still wasn't a strong relationship that would explain the variability in observed turbidity. This led to more in-depth thinking about what processes within the forested watersheds in our study area could be contributing to the increased turbidity measurements. We ultimately landed on a simple explanation: roads. And more specifically, how much of the watershed flowed to a road. This is where hydrologic alteration comes into play. Recall that hydrologic alteration is a term that refers to changes in the way that landscapes control and influence water. The relevant example here is pretty straightforward. As rain falls on a forested hillside, forest cover interrupts and slows water, causing much of it to percolate into the ground, where it is absorbed by plants or continues to move slowly underground towards an aquifer, spring, or waterway. Some small amount of water also runs over the ground downhill. Now, let's put a road on that hillside. Despite the fact that overall most of the trees are still intact, this results in a surprising amount of change. The road and its associated drainage structures, ditches and culverts among other things, accelerate, concentrate, and energize water, dramatically altering the way the water is controlled even in a forested landscape. This becomes even more impactful as the effects from each road add up when looking at a larger area than a single hillside. Given this, SRBC and our partners came up with an idea for a metric: the hydrologic capture zone of a road. The hydrologic capture zone is the area where, if a raindrop were to fall within that area, it is likely to be captured by a road as it moves downhill. More simply, it is the land area uphill of a road. Because they are similar linear features that are increasingly common, we also included pipeline corridors in this analysis. We mapped the hydrologic capture zones in each watershed and then calculated the portion of the watershed that falls within a hydrologic capture zone as a percentage. This percentage provides a window into the stability of the watershed's hydrology. When we compared these percentages to the in-stream turbidity data via a GLM model, a relationship immediately became apparent. Watersheds with high turbidity generally tend to have a lot of acreage in hydrologic capture zones, or to put it another way, watersheds with lots of roads and pipelines, especially low elevation roads and pipelines, have higher turbidity than those with fewer roads and pipelines. This is true even in watersheds with lots of intact forest. This confirmed the hypothesis that roadways built through forested landscapes were having a large impact on in-stream turbidity, but that the placement of these roads in respect to natural drainage patterns mattered. To think of it another way, the results here indicate that a ridgetop road, which would have a very small capture zone, would have a much smaller impact to in-stream turbidity compared to a road built across the slope further downhill. The road built downhill would ultimately capture a much higher volume of water and potentially transport it quickly through its systems of ditches and culverts. As is often the case with science, early results drove this project in a different direction than originally planned. The final results strongly indicate that roads alter natural hydrologic processes and contribute to excess sedimentation across the Susquehanna River Basin. Roads are a ubiquitous part of human life. They are also a permanent change to landscapes that have a measurable effect on water quality. Not all roads are created equally. The location and design of the roads matters. We hope this video has provided some insight on the data and methods at the center of this applied watershed science. These results make a strong case for new best management practices for road building and road maintenance, a subject discussed more thoroughly in our fourth and final video in this series, which will take you into the field with the Penn State Center for Dirt and Gravel Road Studies. For more information about other aspects of this project, be sure to check out the Overview and GIS Techniques videos. Thanks so much for watching.